Okay, we're all here. Let's get going. Did anyone read or see or hear any commentary about the unemployment rate release on Friday that took a frequentist perspective on that realization of the estimator? Did anyone see anything, commentary, etc., about someone who took a Bayesian perspective on that release of data? Does anyone know what the damn unemployment rate is? 4.1. Okay, that by itself, neither Bayesian nor frequentist, but at least we know what it is we're talking about. Do you think any of the people who drove the stock market down 6% in the days following the release of the unemployment rate were taking a Bayesian or a frequentist perspective on the price of stocks? Algorithms programmed by people might have a perspective.
They assume that because unemployment is going down, wages will rise, or that industry will rise. So the stock market went down. So isn't that basic? So assuming the probability of an interest rate going up?
Yes. Now that may only be like part of the story. It could be other things going on, but I would say fundamentally, if you are a person or a bot who, gets new data, so unemployment rate is, whatever it is, conditions on that to make a prediction about what interest rates will be, gets the conditional distribution of what you think stock market returns will be if interest rates were, higher, then, you could see something like that. Now, in point of fact, 4.1 has been the unemployment rate for the past 3 or 4 months, so it wasn't really that unexpected thing. But, I think maybe part of it is, thinking, well, with, the data that's been coming in, the new Federal Reserve chair will be more inclined to raise interest rates at a faster rate in the United States or something like that. So yes, I think that is fundamentally a Bayesian thing. What else? Anybody watch the Super Bowl while you were not looking for economic commentary? Anyone know who won the Super Bowl? All right. So a lot or a little has been made of the fact that the Eagles use quantitative methods more than other football teams tend to do. They're sort of more along the lines of what baseball teams have been using quantitative methods for the past several years. And a lot is made of the fact that the Eagles are more prone to go for it on fourth down than other teams. And I think that can also be seen from a decision theory, expected utility perspective, that, they're looking at it, what is the probability we win the game if we go for it on fourth down, multiplied by the value of winning, plus what's the probability, if we punt on fourth down, what's the probability winning there, etc. And they seem to have different estimates of the probability of winning, given that you go for it on fourth down, than other teams do. And that is fine. That's all consistent with the Bayesian way of looking at things. But it seems to be the case that the Eagles coaching staff and the employees and stuff that they have spend more time and effort trying to come up with the probability conditional probability of winning, given that we do this or that, than maybe some other teams do. So that kind of maps onto decision theory pretty well. Okay, so this week we're going to start or continue, I guess, really talking about explicitly Bayesian principles after we go through the obligatory disclosure thing involving the fact that I work at Columbia University. Columbia seeks grants, or has been gotten a bunch of grants to develop STAN. We're currently seeking an additional $10 million of grants. It's not really directed at you. If you have $10 million lying around before the stock market went down 6%, but no, not really directed at you. Maybe some random YouTube person. But so I also use STAN for business purposes, according to Columbia University policy. Those two things create an appearance of a conflict of interest. I should point out that seeking $10 million in grants in order to pay the people at Columbia who develop STAN and don't teach is not a conflict of interest, because that is through Columbia. It is moonlighting outside of Columbia for more than $5,000 per year that creates the appearance of a conflict of interest. Just want to keep those straight. And Columbia has been very successful at getting grants for the past 6 or 7 years. We've been developing STAN and allowed a lot of people to have a job doing that full time. That party might end if we were unable to keep attracting grants, and so that's why you have to disclose these sorts of things. So the reading for today, I think we get into the so-called puppies book because it has Bayesian puppies on the front cover. That's not so apparent if you just read it online, but trust me, they're there. Guy, psychologist named Krushki, has a number of quotes to go through. So he defines, basically, or says we have possibilities, things that could happen over which we allocate credibility, and those possibilities over which we allocate credibility are parameter values in meaningful mathematical models. And so I think the last part of it, specifying a meaningful mathematical model, a generative model where you have some ability to interpret the parameters in it so that you're putting yourself in the best possible position to express prior information about those parameters and meaningful mathematical models is the important thing. And the possible values for the parameters are represented by this set, generally a continuous set, uppercase theta, and we're letting the parameters be lowercase theta, possibly a collection of parameters rather than some singular scalar parameter. Then in some model, we have a data generating process for some outcome, which will usually denote y, and that leads us to Bayes' rule, which we'd actually been talking about for some time. So the fundamental thing that we're aiming for here is the left-hand side of Bayes' rule, probability density function for the conditional probability of the parameters taking on this or that value given the data that we are about to observe. The left-hand side of Bayes' rule can be set equal to the right-hand side, where we have marginal. What does my thing not work today? Yeah. Oh yeah. Marginal probability distribution for the parameters multiplied by a conditional. So this first prior is generally going to be a PDF multiplied by a conditional probability distribution for the data given the parameters, so y given theta. If y is discrete, then this second term here could be a probability mass function. If y is continuous, then it's going to be a probability density function. But we just write it as f of y given theta either way, and then divided by the thing in the denominator, which goes by many names, but you can interpret it as a marginal probability distribution for the data irrespective of the parameters. And so we can write the denominator as the expectation of the conditional distribution of y given theta with respect to the weighting PDF f of theta, which is our prior, and then integrate theta out in order to obtain the so-called marginal distribution, marginal probability density function, probability mass function for the data. Of course, the numerator, if you multiply it together, implies a PDF for the joint distribution between theta and y, and you can see the denominator is just integrating theta out of that joint PDF in order to get the denominator. And the denominator here is actually the difficult part computationally of doing Bayes' rule, and so we're going to have to come up with ways to do that better. But again, really the denominator is implied by the numerator. It's just the same way that we did, marginalization by summing over the columns or the rows when we were talking about bowling. That was the case where we were talking about discrete random variables. In the case of continuous random variables, like our beliefs about theta, we have to do integration rather than summation, but it's the same principle of marginalizing theta out of the joint PDF for theta and y in order to get a PDF or a PMF for y irrespective of theta. So that's Bayes' rule. And then Bayesian inference is a reallocation of this credibility across the possibilities after you observe new data on y. And this could involve x and other things as well that I didn't explicitly write here. We tend not to write things that appear only on the right-hand side of a conditional bar because it just takes up more space. And so if you represent your prior beliefs about what the parameters could take by a PDF, and then you condition on data that you collect y, that maps your prior beliefs into your posterior beliefs by multiplying your prior PDF by this ratio here. But when we do it with observed data, we tend to take this, even though the mathematics expression doesn't change, into a likelihood function of evaluated at observed data, but considered to be a function of the unknown theta. That gives you your posterior PDF, and then, in principle, you could proceed from there. But all these things that we do that are in some ways approximations of this process or trying to give us the same information of this process really can still be understood through this Bayes rule that we've written down a number of times now. And so that is sort of the fundamental idea of Bayesian inference, reallocation of credibility across possibilities once you get new information about the parameters from the data. So last week, we talked about 3 out of the following 4 ways to actually execute Bayes' rule. The first would be what we did with the Ebola model, etc. Draw from the prior predictive distribution. In other words, draw from the joint distribution of the data and the parameters, in this case, the cure probability, according to your prior, and then keep the realizations of the parameters when the realization of the outcome matches the observed data. So we saw in the observed data there were 5 people cured out of 7 people exposed, and whenever we got a realization of y tilde that was equal to 5, we kept that realization of beta. And so this is very intuitive as to what's going on, how Bayes' rule works. You have this joint probability distribution of beliefs about the cure probability and the number of people cured. And whenever that matches up with the data you're conditioning on, then you keep that realization. So that is very intuitive as to what is happening, but it's really only possible with discrete data that you could get some the realizations to exactly match your observed data. And even if it's possible, it's really only feasible if you have a small number of observations and a small number of parameters. And so this idea is perfect for the binomial model that we were talking about with Ebola. Doesn't work that well in practice in any other situation, but it's a very good conceptual tool for understanding this idea of, okay, we have this prior, and then we're just going to sort of select from, you know, the right part or the left part or the middle part, something like that, according to whether it matches up with the data. And that's our resulting posterior distribution of the parameters. So we're not going to have any other opportunities to use that, but all the other ways of executing Bayes' rule are sort of fundamentally equivalent to this fairly intuitive process in number one. We talked a bit about the second way to execute Bayes' rule last week, which is just to do numerical integration of the numerator in order to obtain the denominator. And this way is good because it follows really obviously from Bayes' rule that we put up on the previous slide. You have a PDF for the parameters. You have a PDF for the data given the parameters. You have some data, and so that second PDF turns into a likelihood. You just do some numerical integration over the space of the parameters to get the denominator. Take the numerator, divide by the denominator, and you have the posterior PDF, the left-hand side of Bayes' rule. And so it's nice that it follows very directly from, or very obvious. All of these follow from Bayes' rule, but the second one I think follows really obviously. But again, it's really only going to be feasible when you have a small number of parameters that you're working with. And even if you have only one parameter, it can be very inaccurate depending on how nice or not nice the function in the numerator is. And that depends on the data that you have. 3 is very similar to 2, except we're going to do analytical integration rather than numerical integration. By numerical integration, I basically just mean do little trapezoids. And R will do something slightly more clever, that it'll make the trapezoid smaller and smaller in the region where the function is changing rapidly, and it'll make the trapezoids wider and wider in the region where the function is changing slowly. And that gives you, could give you reasonable accuracy and reasonable speed. By analytical integration, I mean, work it out like you would with the pencil. This is only going to be possible in special cases where the conditional distribution of the outcome given the parameters comes from the so-called exponential family of distributions. Now, the exponential family should not be confused with the exponential distribution, which we also talked about last week. The exponential family includes several distributions that have a particular form involving e raised to the power negative something in the kernel. So the normal distribution is in the exponential family. The exponential distribution is in the exponential family. A bunch of others, but it certainly doesn't exhaust the possible distributions. And if you get something outside the exponential family that you want to use, it's not going to be possible to do analytical integration. And that's going to be the case if you're dealing with, most of the time, dealing with parameters that are models that have multiple parameters. But analytical integrals are nice because it makes the process of Bayesian learning, which applies, no matter how you do this, very explicit, and it's easy to interpret the parameters as sort of previous data that you may have observed in reality, or maybe just hypothetically imagine using. The fourth way, which we haven't talked about yet, start talking about it next week, is to use Stan to perform so-called Markov chain Monte Carlo in order to obtain draws from the posterior distribution that have a distribution that is governed by the PDF on the left-hand side of Bayes' rule. And that is going to work in a much wider class of circumstances. It will work in principle for any posterior PDF that is differentiable with respect to the parameters. This generality comes at a price, and that it can take a long time for your computer to finish. But that's a price we're typically going to be willing to pay if it allows us to use Bayes' rule for most or all of the situations that we're looking for. Rashika.
And in the previous slide, we integrated over the denominator those methods. On the slide,
Right. So we take the numerator, stick it under the integral sign, integrate over theta, and that's the denominator. So the denominator is the integral of the numerator. Now that is most relevant for 2 and 3. It's sort of behind the scenes for 1 and 4, where we're trying to obtain draws from this posterior distribution that have the PDF on the left-hand side of Bayes' rule. When you do, particularly with 3, it's kind of obvious where these functions are coming from. Actually, obtaining draws is more useful than having a nice mathematical result, because you can do more stuff easily with draws than you can with a PDF. So we'll see it both ways. But basically, in order to do this with appropriate amount of generality, you have to give up on the idea of being able to put these things in closed mathematical forms to actually get the PDF. But what you can do is get draws from the distribution that have the specified PDF. Andres.
You mentioned that in Markov chain can only be used if the posterior is differentiable with respect to the parameters.
Yes.
Could you give an example of like that happened?
So we typically think of the parameters as being continuous. We actually need a slightly stronger condition that this left-hand side here needs to be differentiable, so you can't have like jump discontinuities or something like that in your prior or in the thing. That doesn't exclude that many things. But where it does come in is if you think about your parameters or some unknowns as being discrete. Like you have missing data on, the race variable or something like that. And if you think of race as being discrete categories, and you have, some people who don't respond to that question, they're unknown on that. You might think, okay, I want to do Bayesian inference over the missing data and the parameters, but my missing data are discrete, and that makes it technically hard for Stan to do it. You can kind of work around it, but you have to do more math. So it's something that we'll get to like the last week of the semester, how to make Stan work with things that aren't quite differentiable. Okay, so Bayesians have one of several workflows that they like to emphasize and follow. You'll see different versions of this, but basically the workflow from a Bayesian perspective has, I think, more steps than for other forms of interest. And it's important to go through each of these steps, even though you might see other versions of this. You sort of maybe combine separate steps into two things. But let's sort of say it like this. First, you want to think about dividing your concepts into those that are endogenous versus exogenous to your model. So what are the things that you're trying to explain with your model? What are the things that you're not trying to explain? So for example, with the Ebola thing, we were trying to explain how many people were cured by the drug. That was the endogenous outcome. We weren't trying to explain how many people contracted Ebola. We just took it as given that 7 doctors and nurses, certainly millions of people in Africa, got Ebola, but we're not trying to explain who gets Ebola and when and anything like that. Just taking it as given that 7 doctors and nurses did, then trying to explain how many of them are cured. And then you want to cross that with, is your concept known? So does it correspond to observable data, or is it unknowable? And by unknowable, I don't mean we don't know anything about it, but I mean at best we can hope for is some probability distribution about it that is very concentrated, in which case we wouldn't have that much uncertainty. But there's, for all kinds of things, predictions, etc., we're never going to be absolutely certain, even after doing the analysis, what those things are going to be. So once you have set that up in terms of a generative model, you want to draw from the prior predictive distribution of the unknowns. And we saw an example how to do that. You can then feed those draws back into your software to make sure that your software is working. Becca.
Sorry, can you give an example of the unknowable outcome?
So unknowable would be like parameters.
Sorry, like when we talk about like if the thing that we are estimating is not known but can be described as a narrow probability, like what would be a thing like that?
So if, for example, we're trying to estimate the cure probability of the drug, and we had 7,000 people contracted and 5,000 of them were going to be cured, the posterior distribution for the cure probability is going to be very concentrated around 5/7. But if we only observe 7 people and 5 of them are saved, then we're going to have a lot more uncertainty about what the cure probability is. But this is all the data that we had on people. So either way, we're never going to be absolutely sure.
Yes, there's always
Yeah. But for things that are observed, there are 7 people that we know of who got the drug. So that is a known thing. Question over here? Okay. So draw from the prior predictive distribution. That's useful for a lot of things, making sure your priors are reasonable, making sure that your software is working on this, simulated outcomes that are supposed to be, similar enough to the data that you're proposing to collect, or maybe you already have collected. In the social sciences these days, there's considerable momentum around this idea of pre-registration plans. And so if you choose to do that, you should, have your code ready for how you're going to analyze the data, state what prior distributions you're going to use. And if you're doing that all on simulated data from the prior predictive distribution, then you can kind of mess around with that as much as you want before you sort of codify your plan in your pre-registration proposal. Even if you're not going to do a formal pre-registration, it's good to go through the first steps. Then obtain new data, or use data that you have but you haven't plugged into the software yet, and then use Bayes' rule in order to obtain the posterior distribution of all the unknowables given the known data. When you're using Stan the first time, this will often tell you a bunch of warning messages, and that is a good thing. It's telling you Stan is having difficulty drawing from this posterior distribution as written. You may need to change its settings a little bit. You may need to think about reparameterizations of your models. We'll talk about that more when we get into using Stan more extensively. And then once you have a model that you're reasonably happy with the results and the warning messages have gone away, you want to draw from the posterior predictive distribution using as inputs the posterior unknowables, and critique your model, compare it to the empirical distribution of the endogenous variables that are known. See the ways in which the model is not fitting the data very well. And this is all facilitated by our packages that we have developed. And all of this can be done multiple times if you have multiple models that you're interested in. We have ways of comparing those models using Bayesian techniques. And one thing that is a lot of people like to do, and you definitely should do, particularly when you're starting out, is to start with a pretty simple model. Maybe just do like the first 3 steps with a simple model to where you know it works, and then build up to a more complex one that you actually apply to real data. When doing so, you don't want to let your posterior distribution of the unknowns from one model influence your prior distribution that you use on another model for the same data. But it's perfectly legitimate to allow the posterior distribution to be your prior distribution if you get a second batch of data. But using the same data to change your priors is a bit disingenuous. All right. So an example we want to talk about today might be, what will the price of Bitcoin be, a couple of years in the future. And so we want to start with a simple generative model for the price of a Bitcoin in dollars. And we want to suppose, since, Bitcoin price is pretty unpredictable, we're just going to assume that it's uniform between 0 and some unknown supremum. Supremum being sort of the smallest upper bound on the price of Bitcoin. We'll call that theta, and theta has to be greater than 0. So we're saying the price of Bitcoin is uniform between 0 and some unknown upper bound. And we want to estimate what that upper bound is. The PDF of the uniform distribution over the sample space between A and B inclusive is very simple. It's just 1 divided by B minus A, presuming, of course, that the value is within the sample space. But other than that, it doesn't depend on X. If you plotted it out, it would just be a flat line. And so that is what represents the uniform distribution. So going to this sort of 2x2 table in terms of what's known, what's unknowable, what's exogenous, what's endogenous. So it's good to start with the endogenous but known thing. What's the outcome that you're trying to model? In this case, it would be the price of Bitcoins in dollars, crossing over to what's the exogenous but unknowable, the parameter. In this case, we're looking for the supremum of the Bitcoin price. What's exogenous but known? Well, typically we know what n is, the number of observations that we had. In this model, we don't have any predictors like X, but in general, we would, that we're going to take as known and exogenous. Things that you use to form your priors are going to be considered exogenous and known, etc. So we want to be able to quantify our beliefs about theta, the supremum of the Bitcoin price, using some probability distribution, and that probability distribution may condition on other things that were known. And so when we did this for the Ebola thing, we were talking about, well, what's your prior mode? What's your prior median? When I give you information about the monkeys that were tested for the cure probability, in which case the prior mode, prior median would also enter into this as exogenous but known. And then endogenous but unknown might be predictions of the path for Bitcoin price in the future, your utility function, which, ordinarily, if you're, invested in Bitcoins, what are your returns, etc. These are all going to depend on, the upper bound that we don't know. But if we get a posterior distribution for the exogenous unknowns, we can generate the posterior distribution for the endogenous unknowns, like how much money would I make, if I sold, this or that distance away from the maximum price. Questions about where concepts fit into the boxes still? Yes, Stephanie.
And like a regular basic model you control with some variables, would that that would be that?
Yeah. So, age and race and income and education, usually we're not going to attempt in our model to explain why some people are older than others. you don't really need a model for that. It's just when were you born. Similar, we're usually not going to try to explain why some people, identify one way or another in terms of gender or race, which, maybe you could come up with some sort of model for that, but surveys typically don't really have that sort of information. So we're probably going to take your race and gender as known. It's a little bit more iffy for things like education, income, stuff like that. That's something that you might want to take as endogenous to the thing that you're modeling, but it often difficult to do so with stuff that comes from the general social survey. Okay. So new distribution to learn about, the so-called Pareto distribution, which is a distribution from some lower bound m to infinity. That's the parameter space there. It's often used as a distribution for random variables that have long right tails, income distributions, stuff like that. Certainly, the price of Bitcoin seems to fall in that category, and so maybe this is a reasonable distribution for the upper bound of the Bitcoin price. Now, we're not, in this case, using the Pareto distribution to model the price of Bitcoin itself. We're using this to model the upper bound of Bitcoin price. We're assuming the Bitcoin price itself is uniform between 0 and some unknown upper bound that we're using. So the Pareto distribution has two parameters, the minimum m and the shape a. And so shape parameters are usually difficult to think about. And so you can utilize the fact that the median of a Pareto distribution is equal to the minimum multiplied by 2 raised to the power a over 2. And you just do some math to invert that around. You find the shape parameter is equal to 2 multiplied by the logarithm of the median over the minimum divided by the logarithm of 2. So if you have some idea what is the over-under on the supremum of Bitcoin price, what is the dollar value such that you think there's an even chance that the upper bound is less than this, even chance the upper bound is greater than that. So if that's your H, you can map that into the shape parameter A that goes into the Pareto distribution. A is going to be an example of something that is exogenous and known. So if you know your median, you should know A. CDF of the Pareto distribution, particularly simple. 1 minus the quantity m over theta raised to the power A. And so how will we arrive at the PDF for the Pareto distribution? Yes, and what would that be? If we differentiate with respect to what exactly? What are we differentiating with respect to? Okay, 3 choices, M, A, or theta? Theta. All right. So this particular derivative is not particularly hard, but I'm not going to wait for you to go through it. You can verify that if you differentiate with respect to theta, you get A multiplied by m raised to the power of A divided by theta raised to the power A plus 1 in the denominator. The shape parameter, I didn't explicitly list it here, it has to be positive. So this is going to, PDF is going to be strictly positive as well. Right? So this is our prior distribution that we want to use for theta in this case. So the next step on the workflow is to draw from the prior predictive distribution, and we can do that in Stan. So I'm going to define a function that returns a vector of simulated Bitcoin prices. The vector is going to be of size s. So I want to pass in an integer s as the first argument to my function. I also want to pass in the known values for the parameters, the minimum m and the shape. Those are both going to be real numbers. It has to be positive. So I allocate my vector that are going to hold my prior predictions, check that m and shape are both positive, loop from 1 to capital S, where I draw a supremum from a Pareto distribution, a random number generator with minimum m and shape. And then I'm going to stick into the S element of out a realization from a uniform random number generation algorithm between 0 and the realization of the supremum that I just got. Once I get out through my loop, I'm ready to return it. I'm going to return in sorted order to make it easy to plot. But that is a fairly simple, well, it's a prior predictive distribution for a fairly simple model of Bitcoin prices that it's just uniform between 0 and some upper bound that I don't know, get a realization of the upper bound, let's say it's here, and then draw a realization of Bitcoin price uniform on that interval. If I get another realization of the supremum that's way out here, then I'm going to draw my realization of the Bitcoin price uniform between that interval. And so we do that a whole bunch of times, and we get our prior predictive distribution for the endogenous known that we're going to have data on, and then be able to update our beliefs. So if you call expose stand functions, put this into a text file. It's on Canvas now. This will compile this into C++, give you a function in R called BTC_RNG, and then you can call that function with whatever arguments you want. Let's say we want 10,000 realizations. We put the lower bound is $20,000 and a shape of 2. Now we have realizations from the prior predictive distribution for Bitcoins. Questions about that step of the process? Yes?
How do you want to declare some of it?
Well, S is going to say I want 10,000 realizations of this. So that has to be an integer. The M and the shape, those in principle are real numbers. I can choose values of those that don't have decimal points. But I could have put in 2.5 for the shape if I wanted to.
Will your stand function be S, is it?
Yes, it will, because when you say allocate a vector of size S, if that was a real number with, if that was any kind of a real number, even if it doesn't have decimal points, stand, it wouldn't compile because it says like cannot make a vector of size, 10,000.0. Yes, or in particular C++ being more than R, because stan ultimately gets translated to C++. Other questions about that? Becca?
How do you decide what M and A, as you're running this function?
Right.
But we don't know what the median is.
Right, and so you have to express your median of your beliefs about this thing. Later on in the semester, we might put a prior on H and, do something like that. But essentially, like, you had to choose the median and the mode of the cure probability before you saw the data, just with the information about monkeys. Here, you need to choose M, which is the lower bound, and so that is pretty straightforward. The shape A is more complicated to think about, but if you think about something like the median and then map it into the shape, that can be a good way to go. So your beliefs, basically the idea of this you don't know what the parameters are, and the parameters are unknowable. But it's assumed as part of this process, you know what your beliefs about the unknowables are. And you can quantify them and describe them with probability distributions, such as Pareto. And if the Pareto has 2 parameters, then you're going to have to assert 2 things about your beliefs about the unknown parameter in order to uniquely characterize the Pareto distribution you're using. Nathan, number 1.
So, and just to confirm again, where the median in this case is the median of what we think the supreme number could be, not the median that has anything.
So if you went to Vegas and there was some over under on the maximum price of Bitcoin, what would be the value that you're indifferent between betting the over and betting the under? Okay, so in this case, because Bitcoin price is continuous, we don't have any chance of being able to just draw from the prior predictive distribution, see if that matches the maximum Bitcoin price, and then keeping those realizations. Because Bitcoin price is a continuous thing. It's never going to be exactly equal. So we can't do way number 1 of doing Bayes' rule. We could try to do ways number 2 using numerical integration of the numerator to obtain the denominator. And so we want to, let's say we have some data Y, observation on Bitcoin price last year. And then we can write our function in R. We could do this in Stan, but we'll just do this in R. It's going to take in theta, Y, M, and A and evaluate the numerator of Bayes' rule. But we're going to do this in log units, which enhances the numerical stability of the calculations. And then at the end, we're just going to do EXP of that in order to get it back in probability units rather than log probability units. And so if you take your prior PDF and do the logarithm of this, remembering that the logarithm of a product is equal to the sum of the logarithms, and the logarithm of a ratio is equal to the logarithm of the numerator minus the logarithm of the denominator. Just take all that, do the log, you get this expression here. This, the first part is for the prior, and then the second part for the uniform, the logarithm of the uniform PDF here. We get those. We do EXP of that to put it back into probability units. This is assuming that our observed value of Y is in the range that we specify for our uniform distribution. And then we can call integrate of that function, integrate it from M to infinity, given our values of Y, M, and A. And in principle, that should work. But if you plot the PDF for the posterior distribution and the PDF for the prior distribution, it looks really weird. So in principle, this prior distribution integrates to 1 because it's a valid probability density function. But if the red line, the area underneath it integrates to 1 over this very elongated range of the sample space here, how could the black line have area of 1 underneath it? And the reason why this looks messed up, and it is messed up, is because the integrate function in R cannot integrate this particular kernel function very accurately. It's sort of off by an order of magnitude. It's a small number, but it's, in relative terms, off by a whole lot. And so numerical integration, while it's sort of easy to write down, it can be inaccurate for functions that are not that well behaved, particularly those like, involving Pareto distributions and stuff like that have a very long tail. You have to really integrate it over a long range of the parameter space that has non-zero values. So basically, this black line is totally wrong. So, Lise.
still haven't really understood how numerical integration is accurate.
How is it inaccurate, or how is it accurate?
Why is it so inaccurate?
Yeah, so again, just think about little trapezoids. So if you have a function that is non-zero over just wide interval, and you have to do like so many little trapezoids to get there, if each one of those little trapezoids is like, you know, not totally perfect for a curve, and you have to add up like a billion of them, eventually you can be way off in relative terms. So you see the scale here. We're talking about stuff that's like 10 to the negative 4, but it's the denominator that was calculated here was like off by a factor of 1,000.
So that's like principle about our jobs, like directly like this.
Yeah.
Thing because like I mean, we talk about integration initially, usually like you go to the limits. R just stops at some point.
Yeah. So when you put in infinity, but that's just a keyword for R to be like way over there. So numerical integration, not always perfect, and in this case, imperfect.
What you were saying, analytical is or like, but then I don't get. What's an analytical?
Oh, so we're doing analytical on the next one, which is a lot of fun. And the reason why I know numerical integration on the previous slide was inaccurate is because you can easily do this integral by hand, and you know what the sort of, you don't have to do little trapezoids. You can just do some algebra. So the numerator can be expressed as our prior multiplied by the products from 1 to n of the uniform distribution, assuming your y falls in that interval. We can write this as this, and the denominator changes to theta raised to the power a, which is the shape, plus n, which is the number of observations, plus 1. And so if we go to integrate that thing, we can pull the a and the m out, because this is just integrated over theta. Write the denominator of this like this with everything negated in the numerator. And doing the integral of like something raised to the exponent is the easiest type of integral to do. You can write that as this piece multiplied by that piece there, evaluate it at infinity, and subtract the evaluation of that from m. So if you put infinity here, raise it to the power of a negative number, that's 0. So the first piece goes away, and just subtract this, inserting m for theta. See what that is. You get a result that can simplify to a times m raised to the power of negative n divided by a plus n. And so that is sort of analytically the correct denominator. And that's way different from what R told me when I did numerical integration. Then, okay, here's the numerator, here's the denominator. We just divide one by the other to get our posterior PDF for theta. You divide this by this, bunch of stuff cancels. We can write this in the form a star times n to the a star, all divided by theta to the a star plus 1, where a star is equal to a plus n. And this is the same form as our Pareto prior that we started with. We've just changed to a star from a, and a star is equal to a plus n. And so this is similar to what we saw last week with the beta binomial distribution. That one had 2 parameters. But, you know, when we updated it, we had like a star and b star that depended on y and n. In this case, a star just depends on the shape that we started with and the number of observations that we have. And so this is the same form as the PDF of a Pareto distribution that has minimum m, which is what we started with, and updated beliefs about the shape parameter going into it. And so now we can make the plot correctly, and we see how the PDF corresponding to our prior in red gets shifted to our posterior in black. It still doesn't totally look like these both integrate to 1, but that's just because I chopped off the plot. In reality, the red line keeps going out way like this. And so both of these actually do integrate to one, but we have more concentrated beliefs around 20,000 or so than we did when we started, after observing, you know, roughly speaking, how high Bitcoin price has reached so far of $19,000. Questions about that? Not so much on like, how do I do calculus? You could type that into Wolfram Alpha, but the difference between doing this analytically, which is like exact, and doing this numerically with little triangles, which can work sometimes, a lot of times, but sometimes doesn't. And you wouldn't really know that this was wrong unless you had the analytical result to check it with. And most times you won't have the analytical result to check it with, in which case you could be wrong if you did it numerically but not know. Rashika?
Ideally, when you are comparing the prior and the posterior, what are you expecting to see? Because you don't want them to be the same, like prior and posterior would be different. But like, just if you're trying to judge, what are you?
So you should expect the posterior distribution, which conditions on data, to have less variance, to have more concentration. So here we're representing in terms of the PDF. So, you know, the values near 20,000, much more plausible under the posterior than the prior, having observed Bitcoin price is so far topped out at like 19,000. The PDFs are ratio scale variables. So it's legitimate to take the ratio of one to another. And so this is basically saying, you know, the posterior probability that it's near 20,000, like a very small interval around 20,000, is like 1.5 times higher under the posterior than the prior. And that's due to the fact that we observed a data point that was like 19.
Prior is just assuming the uniform distribution.
No. Prior on theta with the Pareto distribution, and then assuming a uniform between 0 and theta for the price. So it's basically saying like the Bitcoin price is totally unpredictable within some range, but we don't even know how big the range is. Again, that's a very simple model. Nathan, number one.
I was just going to say, so in this case, like updating our information about what the Supremo, or whatever it's called, would be like, so more and more time passes and it doesn't go past 19,000. This is just going to get more and more concentrated over time.
Right. This is going to depend on N. I only wrote in one observation, but yeah. Anyway, this is a too simple model to go out and invest in Bitcoins with, but it hopefully is simple enough for you to understand the intuition of updating with Bayes' rule analytically, and where the analytical solution can be like exactly correct in the easier ways without having to do integrals can be wrong in practice. Robert.
We specify the minimum gas for the Supremo 20,000, or did we just? I missed that.
I did, yes.
Okay.
You could have used some other number. Another question, Christina. Yes. Other questions? Okay. So now the last step in the process, again, you could go into more details about all of these. Draw from the posterior predictive distribution of Bitcoin price, now using shape star rather than shape. So just add in to that, and we get same function that we defined before in Stan. Now we're just calling it with A star rather than A. I divided the price by 1,000 to make this more easy to read, but here we just have the empirical CDF of our posterior predictive distribution for what Bitcoin price will be at any particular moment under our model. And so you can see here, sort of the median of our posterior beliefs is like a few thousand here. And most of the CDF is, you know, between here and I don't know, 30,000 or so. But we have this really long tail. Providing, you know, we don't really have a lot of certainty about what the supremum of Bitcoin price is. And there's at least a small probability that it could be some really huge number. And so for at least one of the 10,000 realizations or whatever that we did, you know, there was a realization of the supremum that was like $1 million. And then a realization of the price that was like 60% of the supremum. And so this runs out to putting a little bit of posterior probability on, you know, the Bitcoin price could be 600,000. Is that seem reasonable to you? Or not just the end, but does the whole thing seem reasonable to you for what Bitcoin price could be in like 5 years? Robert.
Yeah, I think it does. I mean, like almost certainly something within the range it is we've seen before with a tiny probability of something way high. Maybe the probability of something that high is overstated, but like if it's small enough that it seems to ever.
Yeah, I mean, this seems like it has like characteristics of something that might be reasonable. The long tail, that makes sense. The huge, you know, having anything between like 0 and 30,000 basically being quite probable under the model, you know, that kind of makes sense too. But sort of the exact details of this seem a bit extreme. Of course, you know, the actual price trajectory of Bitcoin the past year or so has also been a bit extreme and probably way more extreme than anyone's prior beliefs about that in like 2014. But anyway, you have the opportunity to criticize, you know, whether you think your model is reasonable by evaluating the posterior predictions of it. And we can do this in much more detail when we start adding X and stuff like that. Questions about that or any other step in the process? Okay. So just remembering the likelihood function, talked about this a few times. It's the same expression as a PDF or a PMF, but there's sort of 3 distinctions about a likelihood function. First of all, if we consider this thing to be a function of X, where X is the random variable and theta is something that we're given, whereas with the likelihood function, we reverse it around. We're thinking of the likelihood function as being theta. We can evaluate that at any value of theta in the parameter space, but we're only going to evaluate it at the one observed data point or data vector or data matrix that we have. So if it's a function of X, it's a PDF. It's a function of theta. It's not a PDF. And that, you know, goes along with saying the integral of a PDF has to be exactly 1 or summation if it's discrete. But if we integrate the likelihood function over theta, we're going to get a positive number, a finite number, but it's not going to be 1. So the likelihood function is not a PDF with respect to theta. Also, you know, as we just saw, we often think of the likelihood function to be the likelihood function given a sample of size n, conditionally independent observations. And so the whole likelihood function is the product of the contribution for each of the n terms that we have, and that can be evaluated at any value of theta. Moreover, when we say the likelihood function, oftentimes when we're doing computation and stuff like that, what we really mean is the natural logarithm, which is called the log likelihood function. But people are not always explicit as to whether they're talking about the likelihood function or the log likelihood function. In any event, if this is the likelihood function and we take the natural log of it, the logarithm of a product of positive numbers becomes the sum of the logarithm of positive numbers. And then we get the log likelihood function, which is actually used more often. So just sort of keep those distinctions in mind. So if that other model wasn't really great, it might have had some redeeming value, but it certainly didn't tell us anything about the trajectory of Bitcoin price. And so to have a more advanced model, we might consider an autoregressive model, where the price of Bitcoin today depends on the price of Bitcoin yesterday, and then there's some random innovations to the price of it every day. So the endogenous known is the same as what we have before, but now we have additional parameters that are exogenous unknowns. The autoregressive coefficient, how sensitive the price of today is to the price of yesterday. The expectation of Bitcoin price, mu, and the standard deviation of the innovations in Bitcoin price, get sort of a random draw of the error term every day. Let's have mean 0, but an unknown standard deviation, sigma. And we want to use those parameters to form a autoregressive model. What's known, we might have t observations. We have our beliefs about the parameters, endogenous but unknowable. So utility, of investment that we have before. Another unknowable endogenous value is alpha, which is the intercept of that. This is defined simply as mu times the quantity 1 minus phi. Phi has to be less than 1 for this to work. But in any event, alpha is just the product of these unknowables, mu and phi. But since we don't know mu and we don't know phi, we don't know exactly what alpha is. But we could get a posterior distribution of it. It's not that interesting in and of itself, but it's an endogenous unknown. Questions about that? Everybody sort of heard of an autoregressive model before? Okay. So here's how it would look in terms of drawing from the prior predictive distribution. So first, I'm going to allocate myself a matrix. So I want to have t periods down the rows and s realizations of this temporal process across the column. So what we were doing before, implicitly, we just had like one observation. Now we're going to have t simulated observations, but we're going to do the whole thing s times. So we check to make sure our parameter values are realistic. We start our loop. So the first thing we want to do is draw a value for mu, which is our expectation for unconditionally of the series. We can use the location scale property of the normal distribution that we talked about last week. So we can draw from a standard normal distribution that has mean of 0, standard deviation of 1, scale it up by our prior scale value, which we pass in as an argument to the function, shift it over by our prior location value, and now we have a realization of mu. Similarly, with our realization of sigma, the standard deviation of the innovations, we can draw from an exponential random number generator with parameter 1, multiply that by our expectation, prior expectation for what sigma is. Now we have a realization of our standard deviation. Finally, phi, which for most things in the social sciences, the autoregressive coefficient is going to be between 0 and 1. Technically, it could be between -1 and 1, but we don't see a whole lot of things in the social sciences that have negative autocorrelation over time. So I'm going to restrict this to be between 0 and 1, and consequently, I'm going to use my beta distribution that we used last time for the cure probability as a prior for this autoregressive coefficient with shape parameters A and B that could be derived from my prior mode, prior median, etc. Okay, so with those 3 lines, I've drawn from my prior distribution. Next thing I want to do is obtain a realization from for the 0th value of the time series. So the value before the first time period. And since there's nothing to condition on, this is just going to be a realization of a normal distribution. You can show this mathematically with expectation mu and scale equal to sigma divided by square root of 1 minus phi squared. So we have the realization of the 0 period. We have the intercept, which is just mu times 1 minus phi. We use the realization of the 0 period in order to generate the first period. So this is our intercept alpha plus our autoregressive coefficient phi multiplied by our realization at time 0 plus another realization that comes from a standard normal bumped up by our realization of sigma. And that gives us the price at time 1. Then from 2 to t, we're just going to loop over this, filling in the little t value. Same thing, alpha, phi, but now we're multiplying by the lagged value and giving ourselves sigma multiplied by a normal realization. That fills it up. Loop over S, we're done, and we return out our matrix. And so that is realizations of the prior predictive distribution for an autoregressive process of length t. There's some details in here about autoregressive models we don't have time to go into, but it's the same sort of thing as before. Draw realizations from your priors, use those realizations of the parameters, feed them into your generative model for what you think the data are going to look like, and obtain realizations of hypothetical data, in this case, capital T of them. And kind of a slightly tricky thing about an autoregressive process is, you have to start from the 0th period and you don't have anything to condition on there. But the rest, you're just conditioning on the previous realization. And so we get a model like this and expose it, draw, one value of it from the function that we just defined, and we get a plot that looks like this. So if we had like 100 months or something like that of Bitcoin price, does it look like that? I would say historically speaking, it doesn't, but it could have looked like that. If maybe the market conditions had been a little bit different, it goes up, it goes down, pretty unpredictable fashion, some persistence to it, might be somewhat reasonable as a realization. And, we could feed this back into some other thing in order to make sure it's working correctly. So here is that function of the numerator written in R code. You have to pack everything together into a vector theta if you want to integrate over 3 dimensions. But now we're just calling R functions, representing our prior PDF for mu, our prior PDF for sigma, our prior PDF for phi, and the likelihood, or the log likelihood in this case, which is just going to be the sum of a normal likelihood with the realizations of the data that we put into it. All that is going to be in log units, and then we just exp it to put it back into probability units. So you can see, this function in the cubature package allows you to do integration in multiple dimensions. So the integrate function that comes with R does not. It restricts you to just one-dimensional integration. And the cubature package claims to be able to do integration in a small number of dimensions, not arbitrarily large, but this p-cubature thing, it sort of is claimed to work well if you have 3 or fewer dimensions. And it does work reasonably well on some functions. But on this particular one, it changes too rapidly. It's not a very friendly function to integrate. And this is not only completely inaccurate when you do the numerical integral here, it's also extremely slow. And so this is an example of a model if we wanted to really get the posterior distribution. This would be something that we have to let Stan's algorithms handle rather than trying to do it through numerical integration to figure out what the denominator is. And so, yeah, don't do this. In this case, would not work well. So we've seen sort of the process going through the Bayesian workflow, checking yourself along the way, but also seeing that we pretty quickly, like as in not that complicated models, not that elaborate functions or anything like that, run into problems with the simple ways of trying to execute Bayes' rule. We can't do, prior predictive matching because this is continuous. It would never match exactly. We tried numerical integration, completely inaccurate, and it takes overnight to come up with the answer that's like completely wrong. This particular one, it does not have a closed form integral. So even if I wanted to do it analytically, I couldn't. And so the first three choices right there already gone. The fourth one, which we'll start to learn about next week, is going to work just fine for this and for a lot of other problems. But the first three, they give us some intuition and a way to conceptualize Bayesian updating. But when it gets right down to it, actual use this in a lot of problems for social sciences, those first three ways just won't get the job done almost ever. Okay, so we'll pick it up on Thursday. There's reading that you can download on the syllabus. This guy, Tony Lancaster, taking a economist perspective. We used to use that book in this class. I think it's really good, but the students complained that it was like too quantitative or something. They wanted to read the book with puppies on the front. So we're just going to read the first chapter, but it is really good, and it talks in some depth about different sorts of ways in which you can think about choosing priors and a bunch of other stuff. So read it carefully.